Hi, I'm Mike Fairborn. As a meteorologist, I'm interested in all the ways weather affects our daily lives. One important effect of the weather is its impact on our asphalt or blacktop pavements. Oxidation by the air, rainwater seeping into the pavement, and freeze-thaw cycles in the spring all combine with the weight of heavy vehicles to break up our pavements. And pavement deterioration is very costly. Each year we spend millions of tax dollars to construct and maintain Minnesota's pavements. One of the most important techniques for counteracting and preventing pavement breakup is putting a new asphalt surface on top of an existing pavement. It's called an overlay. I'd like to show you what I've learned about overlays from Minnesota's public engineers and pavement maintenance professionals. They've shown me that given appropriate conditions, an overlay is a cost-effective way to keep our pavement safe, smooth, and strong. In a few minutes, I'll show you the 4 phases of the overlay process. But first, I think you need to know about the evaluation process that leads to the decision that an overlay is necessary. Engineers are constantly evaluating our pavements to determine what maintenance is needed now and in the future. This crew is gathering some of the necessary information right now. They're making a visual survey of the pavement surface condition, and they're drilling down into the asphalt to see how things look below the surface. Thanks. This is called a core, and it's a good one, hard and firm from the top to the bottom. If the material was crumbling, we'd know the pavement was in trouble. Cores are sent to laboratories where tests reveal the strength and composition of a pavement. But cores and surface evaluation aren't enough. I'll show you what I mean inside. Engineers need information about conditions in the layers of the earth underneath the asphalt pavement. They need to know about drainage conditions and the strength of the materials under the asphalt. To do that, they may drill down to get soil samples to test in a lab. And by the way, before they do this, they call the Gopher State 1 call service to find out what utilities are located under or near the pavement. And you should make the same call when you plan to dig anywhere in Minnesota. Here's another method used to determine the strength of a pavement without cutting into the surface at all. The operator controls the equipment with a computer in the van. He raises these weights and then drops them. That simulates the load of a passing vehicle. These sensors mounted underneath the test rig are like seismic sensors used to measure earthquakes. The pavement actually bounces a little bit in response to the falling weight. Engineers evaluate the data from the sensors to see if the various layers are strong or if they're losing their ability to support vehicles. Engineers also want to know if there will be an increase in the weight of vehicles using a given pavement, because every pavement must be designed and built to support vehicles of a certain maximum weight. One pass by a typical loaded 18-wheeler causes about the same amount of pavement deterioration as 2,500 passes by passenger cars. The bridge between information gathering and the choice of a specific maintenance method is called a pavement management system. That's a combination of test data, historical data, and prediction models, sometimes computerized, that engineers use to predict maintenance needs for each section of a road. Here's a typical result. This computer-generated map of Bloomington, Minnesota is color-coded to show the condition of each street. Information like this allows the engineers to recommend the most cost-effective methods. If maintenance isn't done at the right time, costs go up. By the way, the Minnesota Local Road Research Board has produced another video in this series called Road Repair, Do the Right Thing at the Right Time. That explains in more detail the process of choosing a maintenance method for a given situation. For now, let's assume an engineer has gathered the necessary data and is beginning to plan specific maintenance projects. For newer pavements, and when no traffic increase is expected, engineers are likely to recommend preventive maintenance techniques. They'll patch potholes, fill cracks, or apply a seal coat, a thin protective layer of asphalt and crushed rock. When an asphalt pavement gets old, after 20 or 40 years of service, the engineer often decides to remove and reconstruct the entire pavement from the bottom up. It's between a pavement's youth and its old age that engineers commonly decide on an overlay. There are 4 phases in the overlay process. You might call them the 4 Ps: planning, preparation, production, and placement. During planning, an engineer's primary goal is to determine how thick the overlay needs to be. To do that, the engineer reviews design drawings from the original pavement construction, like these. as well as traffic projections, maintenance records, and many other types of information, including the results of coring and surface evaluations like we saw outside. The engineer chooses between two main types of overlays, each used for a different purpose. A functional overlay, usually between 1.5 and 3 inches thick, returns a middle-aged pavement to almost new condition with a smooth, even surface. A functional overlay also protects the underlying asphalt, so strength is maintained. When the overlay must increase the pavement's ability to support vehicles, the engineer chooses a structural overlay, usually 2 to 4 inches thick, or even thicker if extra strength is needed. Besides the decision between structural and functional overlay, another important part of planning is to determine how traffic will move safely during the overlay project. I'll get back to that later. After planning comes the second P, preparation. That refers to preparing the existing pavement for the overlay. One of the most important considerations at this point is drainage. Rain, snow, and ice are really a pavement's worst enemies. Water can damage both the asphalt and the layers of earth that support the asphalt. So engineers design overlays to work as part of the drainage system. That was part of the road's original design. Every road is designed to move water away from the pavement. In rural areas, the water goes into ditches. In urban areas, the water moves through gutters to a storm sewer system. A common method used to reshape the old pavement in preparation for the overlay is milling. That's the process of grinding off some of the existing asphalt. Milling may be necessary to achieve the right shape for drainage, or to lower high spots in order to make a smoother driving surface, or to avoid sharp drop-offs between the pavement edge and the shoulder or gutter. The milled materials, the gravel, also called aggregate, and the asphalt binder, which is a petroleum product, are usually recycled back into the overlay on the same road or are used later in another project. The opposite of milling is patching, which also may be necessary to achieve a smooth driving surface. When surface preparation is finished, all loose material is swept away. There are also lots of details relating to utilities. Where no milling will be done, the level of each manhole has to be raised with a collar like this to meet the new higher pavement surface. Also, the engineer will check construction drawings and other records to be sure all catch basins, water valves, gas valves, and other utilities remain undisturbed during the overlay operation. And that brings us to our third P, production, which refers to formulating and producing the mixture of asphalt and aggregate that will be laid down. While many different formulas are used, it's all called hot mix asphalt, or just hot mix for short. Hot mix is made in about 100 specialized plants like this all around Minnesota. Many factors are controlled at the plant to assure quality in the overlay. For example, the size of the aggregate and the ratio of aggregate to asphalt in the hot mix are carefully regulated. If these factors are correctly controlled, there will be microscopic air spaces between the pieces of aggregate in the overlay. If there were no air spaces in the overlay, the liquid asphalt would ooze up to the pavement surface on hot summer days, and that's not where we want it. The liquid asphalt can cause vehicles to hydroplane over the road surface, and when the liquid asphalt hardens, it reduces the smoothness of the surface. With the planning, preparation, and production taken care of, it's time for placement. Now the engineer puts into operation the traffic routing plan that was devised for the project. There are two major possibilities in traffic routing, and we've all experienced both of them. Either the traffic is routed through the project or detoured away from it. Unless there's a very convenient detour route available, running traffic through the project usually takes less time for drivers, but it's obviously more dangerous for the workers. That's why it's really important to drive slowly through construction zones. Be sure to give construction workers a break. Detouring traffic away from an overlay project may lengthen the public's travel time, but it's safer for the workers, and it allows the work to move more quickly, and that usually saves public funds. While city, county, and state employees perform most pavement maintenance tasks, overlays are generally placed by commercial contractors who specialize in overlaying. During placement, weather becomes important. Hot weather is best because it gives the crew more time to place the overlay and compact it to the proper density before the hot mix cools down. And dry conditions help to assure that the overlay will form a bond with the asphalt layer underneath. Now, as I go through the main steps in the placement process, keep in mind that everything has to move at the right pace to achieve good results. First, a tack coat of liquid asphalt is applied so the overlay will adhere properly. timing is essential for the trucks delivering the hot mix. It's important to avoid any delay that would cause the work to stop, because when that happens, a seam is left in the overlay mat. On the other hand, the trucks have to be timed far enough apart so the hot mix doesn't cool off just sitting around in the trucks. The hot mix is loaded into this monster, a paving machine. The machine has two parts, a tractor unit that mixes and lays out the hot mix, and a screed that levels the surface. The two parts are hooked together by big lever arms on either side that allow the screed to float on top of the mat. The thickness and slope of the mat can be controlled by hand or by automatic leveling devices. The paver operator makes tight joints between adjacent strips of overlay and at the end of each strip. I'm sure you can see that it takes a lot of skill to do all of this simultaneously. As it comes out of the paving machine, the hot mix has about 85% of its final density. The remainder of the compaction is achieved by rollers that come in right after the paver has done its work. Three kinds of rollers are used. First, steel-wheeled rollers with vibrating mechanisms compact the mat efficiently. Then rubber-tired rollers may be used. These provide a kneading action on the surface to achieve a tight, closed texture. Finish rolling is done with the non-vibrating steel-wheeled rollers. These iron out the hot mix to a smooth, level surface. As with every other part of the process, timing is important during rolling. Roller operators have to move slowly enough to achieve the necessary compaction with the right amount of airspace, but they also have to get the work done before the hot mix cools down. Both goals are met by using multiple rollers working at just the right speeds and in predetermined rolling patterns. Last but not least, everything has to be inspected to be sure the overlay has the correct thickness, compaction, and slope. This assures that the pavement will perform correctly throughout its expected life. Recently, there have been some important changes in the quality control process. In years gone by, samples taken from finished overlays were sent to test laboratories, and it often took several days before the results were available. Then, if problems were found, either the contractor was required to take corrective action or the payment was reduced according to the nature of the problem. As you might imagine, this sometimes led to disputes. In the mid-1980s, the Minnesota Department of Transportation began developing a new quality management program to solve this problem for federal and state highway work. The specifics of this program are listed in MnDOT Supplemental Specifications text. On projects run under the new program, mobile test labs are required on work sites. This means that test results are available in a matter of hours or even minutes rather than days, so crews can make needed adjustments right away. MnDOT's program has been very successful and has now been adopted by many cities and counties in the state for their larger overlay projects. The result has been more consistent quality and a better return on our tax dollar investment. Speaking of dollars, in 1994, 1 mile of a 2-inch thick overlay on a 2-lane road costs up to $60,000. That price is affected by many variables, including the prices of asphalt and aggregate and shipping costs for those materials. That's a lot of money, so I'm sure you'd agree it's important to carefully control every part of the overlay process. The most effective way to control pavement maintenance costs is to do each type of maintenance, patching, crack treatment, seal coating, and overlay at the right time. As I said before, there's a predictable sequence in which each of those steps needs to be taken. If any step is put off too long, a pavement's lifespan is severely shortened and the cost to us taxpayers goes up. Well, there you have a quick overview of the overlay process. Since I went through everything pretty fast, I think it will help if I review the 4 P's again. During the planning phase, engineers determine whether they need a functional overlay to improve the pavement surface or a structural overlay to increase strength. Preparation involves dozens of details, including patching, leveling, milling, and utility coordination. The production phase includes both the design and manufacture of the hot mix asphalt under close quality control. Placement is often monitored with the help of mobile test labs. It's a complicated process that takes a lot of know-how at every step, but it's being done with consistent quality throughout Minnesota by our public employees and contractors.